This is the lecturette for sections 11.4 and 11.5, which analyzes intermolecular forces, the forces that hold molecules near one another. And so the first thing we'll do is we're going to itemize the kinds of forces and how they come about, and those are listed here, and talk about their relative strengths. And then we're going to relate those intermolecular forces to all the properties we've been talking about with liquids, and so we can connect molecular structure to those properties to get us to the point where we can actually make useful predictions. So again, to remind you what we're talking about, we've talked about and looked at the fact that if you have a glass of cold water, what will happen is water from the atmosphere will condense on the outside of the glass, and what's happening is these are water molecules, and there's some force of attraction between them that holds them near one another. And so the water molecules are attracted to each other, go into the liquid phase from the gas phase, and it's those attractions that we're talking about. And so here's a summary of the kinds of intermolecular forces we'll be talking about. The first is dipole-dipole forces. I'm not going to go into detail with them here because I'm about to. The next are a special case of dipole-dipole forces called hydrogen bonding. Then there's dipole-induced dipole forces and induced dipole forces. The slides here are mainly to give you a good reference view of this when you're studying. But notice that the values for the strengths of these forces are relatively small. They're like between 2 and maybe 50 kilojoules per mole, whereas a regular chemical bond, like the bonds that hold things together inside a molecule, are much, much larger, 10, 20 times larger than these forces. So they're all weak forces. So let's remember what happens when water boils. What happens is individual water molecules, these are each water molecules, they all separate from one another. So they all become separate. So this is a liquid, and this is a gas. What does not happen is the water molecules don't break up. So that is, that atom and that atom are held together by a chemical bond, and that chemical bond is about 400 kilojoules per mole. It's a little more than that. It's around 400 kilojoules per mole. Whereas this force to break this water molecule from that water molecule is maybe like 40 kilojoules per mole. So it's only around a tenth as strong. So you're not breaking apart individual molecules, you're just removing one molecule from another. Okay, so let's talk about what this is like for particular cases. First thing we're going to do is talk about dipole-dipole forces. And that is you have two polar molecules, and the idea is a polar molecule has a positive side and a negative side. So HCl, the Cl is more electronegative, so it has a partial negative charge. And the hydrogen has a partial positive charge. They're not full +1 and -1 charges. The charge is like around -0.2 and +0.2. And so when you have HCl and you cool it down, what will happen is each HCl will align and try to connect with another thing of the other side. So this chlorine will be attracted to that hydrogen, that chlorine will be attracted to that hydrogen to that chlorine, and you end up making a network of those different atoms. Hydrogen bonding is a case of really strong dipole-dipole bonds, and it happens only when a molecule contains one of these three kinds of bonds. So these are not the hydrogen bonds, even though they contain hydrogen. Those are not the hydrogen bonds, but these lead to hydrogen bonding. And the question then is why? These lead to particularly strong intermolecular forces, and there's two reasons why. The idea is that, let's take oxygen and hydrogen, and remember there's other stuff attached to the oxygen here. The oxygen is very electronegative, so this bond is strongly polar towards the hydrogen, which is very not electronegative. And so this gives a relatively large positive charge there and a relatively large negative charge there. So you have larger positive and negative charges that will be doing the attraction. The second thing is the idea is what we're talking about is talking about, say, a water molecule attracted to another water molecule. And so the attraction is there. So you've got this relatively large positive charge there, relatively large negative charge there. But the other thing is that the hydrogen is small. Hydrogen atoms are small atoms. And so what happens is that's a short distance. And so the combination of the short distance and the strong polarity of that bond leads to particularly strong interactions between those partially positive and partially negatively charged atoms. So the way you tell whether hydrogen bonding is possible or not is you just look for these bonds inside a molecule. The FH one is easy because the only molecule that has an FH bond is HF. But the other ones, there's lots and lots of molecules that have either OH bonds or NH bonds. So the top molecule, propanol, does have an OH bond. It's right there. So this can form hydrogen bonds, and the idea is one propanol molecule will hydrogen bond with another propanol molecule. Dimethyl ether has oxygens and hydrogens, but it does not have an OH bond. There's no hydrogen connected to an oxygen. So this cannot do hydrogen bonding. And so what we can do is we can look at which things are stronger and which things can hydrogen bond. Notice that we have this strong hydrogen bond here, and that's on the order of around 35 kilojoules per mole, just roughly. The bond here is around 400 kilojoules per mole. So what happens is when you separate these things, if you take these two ethanol molecules and pull them apart, that's the bond that will break. Those stay intact.
And thereby induces a
Next,
dipole
we're going to talk
in
about
the O2.
dipole-induced dipole molecule.
This shift allows O2 to be weakly attracted to the water
cases.
molecule.
So I'm going to
On average, the electron
stop playing that. So what happens is we have a water molecule, and so let's say we have a pool of water, a glass of water, and we have oxygen molecules. An oxygen molecule, O2, is nonpolar. So now we have a polar molecule and a nonpolar molecule. So we've got an O2, it's nonpolar, and we have a water that is polar. So the water's got a partial negative charge there, it's got partial positive charges on the hydrogens. When they approach each other, what happens is
cloud of an O2 molecule is
and water get near
distributed
each other, the
symmetrically
negative
across
charge
the
on
molecule.
oxygen
The molecule is
will
not polar.
cause a repulsion
A water
of this
molecule,
side
which
of the
is
electron cloud
polar,
of the,
repels the
of
electron
oxygen
cloud,
2
causing
molecule
it to be
and push the
asymmetrically
electron
distributed
density.
and thereby induce.
It pushes the electron density on this side over there because this partially negative charge is repelling the electrons. So what ends up happening is this is still partially negatively charged, but it induces a polarity here. It induces a dipole here. So this now has
Is a dipole in the O2. This shift allows O2 to be weak.
this now has a partial negative charge there. I can't really draw into this part. A partial positive charge here and a partial negative charge here. So it makes the O2, when it gets near the water, it induces a dipole there. So that's an induced dipole. Dipole means just the polarity of the molecule. And so this force is called a dipole-induced dipole force because it's formed between a polar molecule that already has a dipole and an O2 molecule that does not have one but gets one when it approaches the water.
An iodine molecule
also
has,
have
on
two
average, an electron
nonpolar
cloud that
molecules.
is symmetrically spread over each iodine atom.
Two
I2
nonpolar
is not
molecules,
polar.
they shouldn't be
The
attracted to each other at
attractions
all
or
because they're both
repulsions between the
nonpolar.
atoms
But
of
when
I2
they
molecules
approach each other,
can distort
what
their
happens
electron
is they
clouds.
also form,
Dipoles can thereby be
a
induced
situation-
momentarily in neighboring
a situation where what happens is there's a momentary polarization of one of the I2 molecules, so it gets a little more negative charge here. It then repels the electrons here, which pushes them over there, and now we have two I2 molecules where you've got a negative partial positive charge there, partial negative charge there. Another iodine molecule where you have a partial negative charge here and a partial positive charge here, and then you have an attraction between those two because they have two different opposite charges. The reason this happens is the molecules are just more stable when that happens. By doing this polarization, it leads the molecules to have this extra attraction, this extra interaction, which is favorable, and that's what then transposes. So I2, even though I2 is completely nonpolar, it actually exists at room temperature and pressure in the solid state. So that's an induced dipole force. It's also called a dispersion force, and also called a London dispersion force. So the word London is sometimes precedes dispersion. Oh, look, it says so right here. All right, so now we're going to return to the properties of liquids and relate those to these different kinds of intermolecular forces. So remember the different properties we've had are enthalpy of vaporization, which is how much energy it takes to pull molecules apart from the liquid phase to the gas phase. Vapor pressure, how much the tendency of the liquid molecules to escape into the gas phase and therefore exert a gas pressure. Boiling point, the temperature at which the vapor pressure reaches external atmosphere. In this particular case, we're going to talk about normal boiling point because we can compare different compounds under the same conditions when we do that. And then there's surface tension, the tendency of a liquid to resist change, and also viscosity. So we're going to relate these different kinds of intermolecular forces to these different properties. So as we've talked about before, as intermolecular force strength increases, what will happen is the enthalpy of vaporization will increase, vapor pressure will decrease because fewer molecules in the gas phase, boiling point will increase, you need to use up the temperature greater to get the vapor pressure to reach atmospheric pressure, and surface tension will increase with increasing molecular forces, and viscosity will kind of increase, but oftentimes not. There's not a very good strong correlation there. And so to remember, the way we decide which kind of molecule has stronger intermolecular forces, we look at those properties. And so what happens is in this glass of, I think it's brandy or whiskey, there's a mixture of water and ethanol here. And both of those can hydrogen bond because they both have OH bonds. But when it's warm, what happens is you find that the ethanol is evaporating, vaporizing, and then recondensing up here. The water stays put. The water stays down in the liquid, which means that this ethanol has a higher vapor pressure. And so because ethanol has a higher vapor pressure, you know that water, therefore, has the stronger intermolecular forces because it has the lower vapor pressure. And so that's essentially the kinds of experiments you do, although this is a relatively trivial one. Okay, so what we're going to do is we're going to talk about trends that we see. And the first trend is trends having to do with dispersion forces. And so we looked at I2, which normally has no dipole, it's nonpolar, but when two of them come near each other, they induce dipoles to each other. This happens from the molecules getting their electron cloud polarized. It goes from nonpolar to polar. So this process of going from that to that is polarization. And the tendency to do that is polarizability. And that's actually a measured property of molecules and atoms, like electronegativity or size or ionization energy. Polarizability increases with increasing atomic or molecular size. So if you think about, say, an argon, which is atomic number 18. So the charge on the nucleus is 18. It has 18 electrons. And you think about a helium, which has atomic number 2, and it has 2 electrons. If you were to polarize, say, a half an electron's worth of charge from one part of the atom to the other, that would be 25% of the half an electron's charge would be 25% of all of the electron density around a helium, but it would be a tiny percentage of the electron density on an argon. The other way to think about it is argon's outermost electrons are less tightly held. And if those outermost electrons are less tightly held, it's easier to kind of push them around and move them to one side of the atom or molecule than the other. And so what we see is that the bigger a molecule is, and the more massive it is, in general, the more electrons it has, the easier it is to polarize it, and the dispersion forces go up. So if you go from helium to neon to argon, those are all the same kind of atom. They're all just single monatomic atomic gases. And as you do that, the enthalpy of vaporization also goes up, you see. And the boiling point also goes up. And so as size goes up, intermolecular force strength goes up. And in general, when you go, say, to diatomic molecules, N2 to O2 to Cl2 to Br2, in general, as the molar mass goes up, the enthalpy of vaporization goes up, and the boiling point goes up. So that's the important trend for dispersion forces, intermolecular forces having to do with induced dipoles. So as molecular size increases, IMF strength increases. Okay, now let's look at a set of molecules that also is related to this, and those are organic hydrocarbons, molecules made of just carbon and hydrogen. And again, we see as size increases, so these are larger, enthalpy of vaporization increases, boiling point increases. And so again, as molecular size increases, IMF strength increases. So these are all for nonpolar molecules. Now let's talk about dipole-dipole forces and relate that to, that is for polar molecules, and relate that to the intermolecular forces for nonpolar molecules. So if we look at two different molecules of roughly the same molar mass, here, or here and here. So N2 and CO both have molar mass of 28. The CO is polar. The N2 is nonpolar. And what we see is that the CO has a slightly higher boiling point. So it has slightly stronger intermolecular forces. When we look at SiH4, it has a molar mass of 32. pH3, it has a molar mass of 34. The pH3, which is more polar, or is polar, has a significantly higher boiling point. And again, we see in this case where you have similar molar masses, the polar one has a higher boiling point than the nonpolar one. So polar forces are dipole forces. Dipole forces are stronger than induced dipole forces. But the effect isn't really very large unless there's hydrogen bonding. So if we look at a series of compounds of hydrogen, and so remember that if you look at group 6A of the periodic table, it's oxygen, and then sulfur, and then selenium, and then tellurium. So if you look at the periodic table, that's the way it is. What you see is that if you look at just the period, so this is period 2, period 3, period 4, period 5. So as you go this way, the central atom is getting larger. And so here you see, as the central atom gets larger, the boiling point goes up. And so this goes along with the dispersion forces. Dispersion force trend. Larger molecules, stronger molecular forces. But when you get to water, if you extended this trend down here, you'd be down around here. But in fact, water's boiling point is way up there. That difference is 200 degrees Celsius. And that difference of 200 degrees Celsius is all due to hydrogen bonding. Because water will hydrogen bond, because it has this strongly polar OH bond and the oxygen small. H2S does not hydrogen bond. And so hydrogen bonding has a huge effect in terms of intermolecular force strength, far, far more than just regular things being polar. It's another case for that. We have two molecules here that are isomers. Isomers are two molecules that have different shapes but the same atoms, same formula, therefore same molar mass. Ethanol has an OH bond, so it can hydrogen bond. What happens with dimethyl ether is it's polar, but not very polar. It's mildly polar because it's got this negatively charged oxygen here, or partially negatively charged oxygen here. It can't hydrogen bond, and so without hydrogen bonds, its boiling point is minus 24 degrees Celsius. Ethanol that can hydrogen bond has a boiling point of 78 degrees Celsius. So again, it's a change of over 100 degrees Celsius in terms for that. Okay, now it's important to realize that these effects are kind of additive, and that we have the dispersion effects of just bigger molecules have stronger forces, and we also have polarity effects, in particular things that have OH or NH bonds in particular are particular strong hydrogen bonds. But lots of times you have molecules that have a really large nonpolar portion. And so this is governed by dispersion forces. And this is governed by hydrogen bonding, this little area here. And it turns out that both of those have important functions in the molecule and how it acts. But in this case, this part is so much larger, the boiling point for this, or the melting point, or the enthalpy of vaporization, is going to be more controlled by this giant long chain, even though it's nonpolar, just because it's so large, its effect overwhelms the single hydrogen bonding group.